Hey everyone. So now we're going to start section 6.4. In the last couple of sections we gave you an introduction to trig. You had trig ratios, elementary trig ratios, sine, cosine, tangent, cosecant, secant, cotangent. We got into a bit more of the weeds in 6.3 when we learned to evaluate trig ratios at specific angles that were bigger than 90. Now, all of this is really useful in certain applications of trig. What 6.4 does is it adds an extra layer of not complexity but definitely usefulness when you're trying to evaluate certain trig scenarios. So 6.4 deals with inverse trig functions and right triangles. We learned throughout the course what an inverse trig function was, right? Or I'm sorry, an inverse function was. So the whole idea of an inverse function was it helps us map backwards. If a direct rule were to take an input from set A and map it to set B, right? Let's say I were to f the input x, apply the f rule, I'd get the output f of x. The inverse would have taken that output f of x through the inverse rule and mapped me back to the input x, right? So if the first rule is take one step forward, the inverse is if I take my result from that step and apply it to another rule called an inverse, it should map me back home. And that's the point of these types of analyses. So we can do the same with trig. The point of the first slide is not to confuse you, but it's just to say, in order to be able to have an inverse, your function needs to be one-to-one, right? One-to-one means it passes a vertical and a horizontal line test. Unfortunately, trig ratios will not pass a horizontal line test unless we restrict the domain. Why is that? Because we have coterminal angles. We discussed what coterminal angles were. Let's say I had an angle that was 20 degrees. Well, if I add a full cycle of 360 degrees to 20 degrees, that would give me a 380 degree angle. That has the same starting and ending points as a 20 degree angle. As a result, if I took the sine of 20 or the sine of 380, it would be the same value. And we learned that through last class because the reference angles are the same. The sine of 380, we'd have a reference triangle that had a 20 degree angle in it. So we'd get the same exact value. As a result, if I plugged in 20 degrees or 380 degrees to my inputs of the sine rule, if the rule was sine, the sine of 20 and the sine of 380 would map to the same rule. That would make it impossible for me to use a backwards rule to map back home. How would I know? If the sine of 20 gave me a value and the sine of 380 gave me the same value, so I was mapped to the same value, if I applied an inverse rule, how could I get back home? How would I know if getting back home got me to 20 or it got me to 380? It would be difficult to tell. As a result, we have to limit our domain. That's what the first slide here does. And I know I've been talking a lot, but this is really just purely theoretical. We're going to get into the mathy portions of this in a second. But what we're doing is we're limiting the domain to say, okay, let's assume that the domain is up to 360 degrees, let's say, just so that we can even talk about the concept of a trig, inverse trig function. Let's only look at angles between 0 degrees and 360 degrees. And what are they going to be called? They call them the arc cosine, arc sine, and arc tan functions, the inverse functions. So we usually had an f inverse written as f to the minus 1. So here we're going to have sine inverse, cosine inverse, and tan inverse functions as tan to the minus 1. Again, this does not mean 1 divided by the sine of x. It does not mean that. The inverse function is not the same as saying it has a negative 1 in the exponent. Okay? The inverse sine means what? Well, let's take a look at the next slide, slide 99. The sine, cosine, and tan functions are restricted on the domain. Sine -1 of x, or arc sine of x, means what? So if the sine of an angle gave me a ratio of sides which were opposite over hypotenuse, the inverse sine of opposite over hypotenuse. So I'm now using the input to the inverse, which was the result or the output of the forward rule. So the sine of an angle is opposite over hypotenuse. Well, if I had two pieces of a triangle that were opposite over hypotenuse and I wanted to know the angle, the inverse would let me solve for the angle. And that's the point of inverse trig. Inverse trig ratios let you find the angle if you know the sides. If the sine of the angle is opposite over hypotenuse, the inverse sine of opposite over hypotenuse should give me the angle. Same with inverse cosine. Cosine of an angle gives me the adjacent side over the hypotenuse side. Well, let's say I had the adjacent and hypotenuse sides, but I had no idea what the angle was. You could use the inverse cosine function and plug in the ratio of sides to then get the angle. That's the beauty of inverse cosine, inverse sine, inverse tan. So I have an example here that says find the inverse cosine of a half. Find cosine inverse of 1 over 2. What this is telling me is, hey, I have an angle theta. The adjacent side is 1. The hypotenuse is 2. Please tell me what the angle is. Well, we can use our graphing calculator, but I could also go further and say, well, we know a special triangle that has ratios of sides 1x, 2x, and x root 3. If I were to use Pythagorean theorem, I would get x root 3 for this side. That happens to be a 30, 60, 90 triangle where theta would be 60 degrees because it's opposite to x root 3. So if I found the cosine inverse of a half, that should be 60 degrees. We can use our graphing calculators here. How would we use the inverse cosine function? Well, you see how we have sine, cosine, and tangent? Right above cosine, we see cosine to the minus 1. That's your inverse cosine function. So I do second, and then my inverse cosine function. You see the cosine to the minus 1 that appeared. Cosine to the minus 1 of 0.5, or 1 divided by 2. So I'm putting in the ratio of sides. That should spit out the angle of 60 degrees. Again, that's assuming that your calculator is in the right mode. So if you go to mode, where is it? Right here. If we go to mode, I'm in degree mode. That's why it gave me 60 degrees. If you were in radian mode, you would get a weird decimal because 60 degrees is pi over 3. So it would do 3.14 divided by 3. Okay? So we can use our graphing calculators to help us here. And a lot of times we will end up using our graphing calculators. But the point is, the inverse cosine is saying I have a ratio of sides, please tell me the angle. Now only when those angles correspond to our special triangles will we really be able to use the special triangles and not our calculators, but almost always you're going to end up using your calculator for these types of problems. Let's look at slide 100. It has a couple of problems. A 40-foot ladder leans against the building. If the base of the ladder is 6 feet from the base of the building, what's the angle formed by the ladder and the building? Okay, so here's a building. And we have a 40-foot ladder. This 40-foot ladder leans against the building. The base of the ladder, so here's the base of the ladder, is 6 feet. So that's 6 feet from the base of the building. And it's a 40-foot ladder. Okay. What's the angle formed by the ladder and the building? So they're asking me for theta right here. Well, technically for theta, I have the opposite side. And if the building and the ground are perpendicular, which hopefully they are, it's not the Leaning Tower of Pisa, then I know that the opposite side is 6, the hypotenuse is 40. Technically the sine would give me the opposite over hypotenuse, so I'd want the inverse sine of 6 over 40. If I use the inverse sine of opposite over hypotenuse, it should give me that angle. Not a special triangle here. So I'm going to go into my graphing calculator and do second sine, which is the inverse sine. 6 divided by 40, close the parentheses, and we get 8.6 degrees. So the angle measure of theta is 8.6 degrees. That would be my answer. Let's look at the second example. So these examples are invoking our inverse function property. What is the cosine of the sine inverse of 3/5? So for these, this is a favorite problem on the final. I'm putting down the graphing calculator. You don't need it. You don't need it at all. You can find the cosine of the inverse sine of 3/5. You can do it on your graphing calculators, but in theory you wouldn't get full points. You can do this algebraically all the way. The inverse sine, if you think about it, of a ratio of sides would give you an angle. Then we're asked to find the cosine of the angle, which would give us a ratio of sides right back. So I never really need to find the angle. We'll see what I mean. The inverse sine of 3/5. Well, you can draw a fake triangle and say, okay, if I had an angle theta and this was 90 degrees, I need the inverse sine of 3/5. So the opposite side is 3, the hypotenuse is 5. If I did this in my graphing calculator, I'd get an angle measure for theta. But then, I would just want you to find the cosine of that angle measure. The cosine gives you the adjacent side over the hypotenuse. So the cosine of an angle is adjacent over hypotenuse, where the sine of an angle is opposite over hypotenuse. I know that the opposite over the hypotenuse is 3 over 5. Can't I find the adjacent side and just say what the adjacent over hypotenuse would be without a calculator? Absolutely. If I know 2 out of 3 sides of a right triangle, I can use a rule called the Pythagorean theorem, which you all should know, to say 3 squared plus my adjacent side squared is 5 squared. Nine plus a squared is 25. A squared is 16. So a is 4. If a is 4, cosine of theta should be adjacent over hypotenuse. 4/5. I never had to know what that angle was. Never had to solve for the angle. It didn't matter. Right? So that's my point to you. For these problems are interesting. There are real world applications. You will get a few of those through your assignments. You actually never have to find what the angle measure is in some of these cases. Here they're explicitly asking you for an angle measure. Here I never had to find the angle. I just wanted to find the trig ratio of the inverse trig ratio. So I didn't need the angle to do that. I just needed the third side. Alright? Again, if you guys have any questions, let me know. Slides 98, 99, and 100 were all on 6.4. The next 3 slides are replicating, so we're going to omit them because I printed the same slides out in the deck twice. But if you have any questions on anything that we did in Chapter 6, please reach out. We're moving on to chapter 5 after this. Take it easy.